Hello everyone, and welcome to our third weekly discussion session for the Physics of Nanoscale Devices NPTEL course. I'm Jyotishwaran, a PhD scholar from the Department of Electronics and Communication Engineering from IIT Roorkee. So, today's session we shall only be covering two topics, that is density of states. This will be for uh, 0, 1, 2 and three-dimensional systems, and then we shall be looking at the Fermi-Dirac distribution. So this is pertaining to the contents of the lectures in week 3 of this course, the assignment for which will be due in the coming week. So moving on to the first topic of today's discussion, density of states. So the density of states, it's a function, it is a density function, and it represents the number of energy states a quantum system has between energy value E to E plus dE. So here E and E plus dE, these are values of the actual energy. Now to understand what this actually means, we need to know about a particular behavior of quantum systems. So this is something that we know, but nonetheless it needs to be re-emphasized. The spacing between the quantized energy levels of a quantum system generally depends on the size of the quantum system. So increasing the size of the system decreases the spacing between these energy levels. So that implies the energy levels come closer and closer and closer as the size of the state increases. Meaning, initially, if I have a system like this is just a schematic diagram, if I have energy levels that are like this, the spacing and all of those things need not be taken as representative. So let me say this is energy level E3, E2 and E1. E2 and E1. Then what will happen is, if the size, like the volume, or rather, yes, so rather than saying, when I say size here, what is meant is the volume of the system. So now when volume increases, what will happen is, energy is increasing in this direction. What will essentially happen is, the energy levels themselves may move above or below, like these energy values may increase or decrease. That I'm not commenting on. What will essentially happen is, they will come closer. Like previously I had an energy difference that was this high, now it is going to be much smaller. So essentially the volume V, it's not the voltage here, when V increases, delta E typically comes down. So this is more or less true for all quantum systems. There are some exceptions, but we need not care about them. All the systems that we shall be dealing with follow this trend. So with that, let us move on to just 1 second. Yeah, let us move on to the first problem. So we consider an 1D infinite square well. This is just a 1D potential well, another way of calling it, as I've mentioned before, and calculate the following quantities. So the difference between two consecutive energy levels in the system. So let me insert a new slide and start the calculations for this question from that point. So where's it going? Yeah. So now we are looking at problem 1A. So what is question 1A? Question 1A says, in an infinite, so yeah, let us, before starting with 1A itself, let us write something. So when we are considering a 1D potential well, of course of infinite depth, then first thing we need to know is all states are bound states. There are no free states in this because the well has infinite depth. So even if a particle in this well has infinite energy, it will not be able to escape, a particle will need to have infinite energy to escape from this well. Otherwise, it is going to be bounded within the well, which is why the wave functions we got were also like bounded wave functions, like they were non-zero only for a finite region in space, only where the potential is zero. Everywhere else the wave function goes to zero, which implies the quantum particle cannot exist in those regions of space. So all states are bound states. So this is something that comes from our first discussion session. And just 1 second. Yeah, continuing. And then what we know is En, the nth energy level, is given by this expression: n squared pi squared h bar squared divided by 2m L squared. So L is the width of the well and m is the mass of the particle, and we know n is 1, 2, 3 and so on. So these are the allowed values of n. So now question 1a asks us to find the energy difference between two consecutive energy levels. Implies what we need to find out is En plus 1 minus En. So this is the quantity that we have to find out. So just substituting n plus 1 in this, we will get n plus 1 squared pi squared. Oh yeah, there is a square over here also. H bar squared divided by 2n L squared minus n squared pi squared H bar squared by 2n L squared. Outside of the parameters that are dependent on n, everything else is common. So we can just extract that out. So the difference will come out to be n plus 1 the whole squared minus n squared into pi squared by 2ml squared. So this quantity will be equal to 2n plus 1, because this is n squared plus 2n plus 1 minus n squared, so those 2n squares will cancel each other out, and so what we will be left is 2n plus 1 pi squared h squared h bar squared, not h squared, divided by 2ml squared. So before going any further, what we can see is all the energies associated with this system can be defined in terms of this quantity here. Essentially, I can alternatively write, let me use a different color, to say that En is equal to n squared E naught, where E naught is this quantity right here. So, and if you can see, even the energy difference between two states again is some function of n multiplied by this quantity E naught. So even this can be written as 2n plus 1 times E naught. So usually when we are looking at quantum systems, it is also true for classical systems, but it is more so for quantum systems. We will be able to find an energy value that is related to all other energies that is defined in the system. So such quantities are called the characteristic energy of the system. So essentially, if I were to tell you this value, then for all intents and purposes, you will be able to solve many problems in this question. So even if I don't tell you what m is, what L is, if I can tell you this value, then you will be able to find out the value of the nth energy level. You'll be able to find the difference between these energy levels, and therefore one can see what the transition energies are and things like that. So this quantity is what is called the characteristic energy of the system. So this is the first part. The second question is, explain the variation of the above quantity at higher energy levels. So essentially what is asked is, as n tends to infinity, like the short version of this question is, oh no, I need to change color. Let me just undo here. And so, you know what, I'll just insert a new slide over here. Yes. So, yeah, I'm far more comfortable using my mouse for these things rather than the stylus. Yeah, so problem B, we have to find the variation of the energy levels, or not the energy levels, the variation of the difference between energy levels at high values of n. So what happens is, the quantity we know delta E, I can technically put a subscript n over here. This means the energy difference between n and its immediate highest value. So that is equal to 2n plus 1 E naught. E naught has been defined in the previous slide. So what happens as n tends to infinity? So as n tends to infinity, we can see that clearly. Yeah, so I seem to have a question. Okay, so I got the request to solve some assignment questions in week 3. I'm not allowed to do that, because that means I will be telling you the answers to the assignment questions. Since the assignment is a part of the evaluation, I cannot directly solve those questions. However, what I will do is this. Every problem that I'm usually discussing in these sessions is related to the assignment questions. So if you can just pay attention to this, you should be able to solve. And that is the thing, not each and every question does not correspond to an assignment question. In between, every now and then, there will be something that maps to an assignment question. So please pay attention to that. That is the best I can do. If I do anything more, someone can, because these videos are being uploaded, I will be held responsible for leaking assignment answers. So I cannot do that. So I'll keep that in mind. However, I can solve previous week assignment questions. So if you have any doubts from previous week assignments, you are more than welcome to ask me. But don't worry, at least for week 3, if you can follow whatever is being done today, then you should be able to answer all the questions. That I can say with confidence. Okay, so moving on with this problem. So as n tends to infinity, this quantity delta En also tends to infinity. Oh, oops. Also tends to infinity, which implies at very high levels, the consecutive energy levels become farther and farther and farther apart as n increases. Okay, so that is the answer to part C, part B. What is part C? What happens to the energy difference when the width of this well is doubled? So what happens when the width of this well is doubled? So essentially what we are given is L goes to twice L. Then what happens to delta En? Now this is why I defined the characteristic energy, because characteristic energy goes as 1 over L squared. So if L becomes 2L, this will obtain a factor of 1 by 4. That implies E naught will become E naught by 4. Okay, so delta En goes to what is the question. So first we know L going to 2L means E naught will go to E naught by 4. This implies delta En will go to 2n plus 1 divided by 4 into E naught. So this is what I represented here in this slide. As the volume, as the size of this system increases, the spacing between the energy levels will come down. And this is important. It is important to understand this to understand what density of states is. Okay, so now you will see how this quantity plays, this phenomenon plays a role in the density of states. So what I'm going to do is, like if you've seen from the slides, you will see that density of states for a 3D system has been derived over multiple classes, and then the 2D density of states was covered in like the following 2 lectures, because 3D density of states was technically covered in week 2 itself. What I'm going to do is the opposite. I'm going to spend a lot of time on the 1D density of states, and then I will give you some hints on what's happening for the 2D and 3D systems. So that is going to be problem 2. So in an 1D square well, again infinite, we need to plot a graph. We need to plot the number of energy states that are found at or below a given energy level, a given energy value. Now what is this? We'll see. And after plotting this, we need to identify the function corresponding to this graph. Okay. Situations, yes. And then we will use this graph that we have plotted and this function that we have obtained to get the density of states function for a 1D system. So the derivation of the density of states can also be done graphically, at least for a 1D system. So we are going to do that for the next few minutes. Okay, so let me again pick up a new slide. Get rid of these text boxes. Yes, so A. Now it's a 1D infinite well, so I know En is again n E naught. I'm no longer going to bother, sorry, n squared E naught. I'm no longer going to bother with the full expression. Any well is going to have a characteristic energy, and every subsequent energy level is given by this expression, where n is equal to 1, 2, 3, and so on. Okay, so now first we need to plot the number of energy states found at or below a given energy level. So what does this mean? So what this means is the following. First I will have a y-axis. Even with lines on the slide, I'm unable to draw a straight line. And yeah, let me keep it around. Shall I make it slightly longer? Yeah, let's see. Let me use the full length. Why not? Okay, so now this is the number of states, n. So this is number of states. So yeah, people who are attending this session live, if you have any queries from the previous assignments, please feel free to ask me. I'll be more than happy to answer them. So this is the number of states, and over here, E, energy is increasing in this direction. This is the origin for this graph. So this is going to be 1, 2, and 3. Like we can also go all the way up to 4, 5 and whatnot, but 1, 2, 3 should be enough for this. So this is the energy. So E equal to 0, there are no states because n starts from 1. So the lowest energy value, and yes, So what I'm going to do here is I'm going to mark ticks over here for E0, 2E0, 3E0, 4E0, 5E0, 6E0, 7E0, 8E0, and 9E0. I'll also have a 10. Not going to make much of a difference, but that is fine. So yeah. So what we need to find is number of states at or below a given energy level. Okay. So at E equal to E0, we definitely have one state where n is equal to 1, but there is no state below that. So the value of our function is 1. Then at 2E0, nothing changes, it still continues to be 1. At 3E0, it continues to be 1. At 4E0, however, n equal to 2 occurs. So I will have the state n equal to 2, and below that I have n equal to 1. So the value of that function will be 2. The number of states at or below this. Similarly, I will move all the way up to 9, because the next is n equal to 3, where the energy value En is 9E0. So at 9E0, we will have this value 3. The next will occur at 16E0. So this is easy enough to understand. So this is the graph. This is the point distribution. Now what I'm going to do is, I will give the reasoning for that in a minute. What I will do is, I will join these lines with a curve. Okay. And I'm telling that we can, oh, it's sloping too hard. It's actually supposed to be almost straight. Yes, so it's going to be something like this. And I mean, it won't become flat. We need to remember that. It's not going to be flat. It will continue rising, like it's an increasing function. So it will kind of have, yeah, very bad at drawing, so I'm like, it will take me that much time to, yes, more or less. It will continue to rise, so understand, that much is understood. Okay, I'm not going to redo this. Now what is the function corresponding to this? So what is happening here? So we know that, let me just slide. So part B is, we need to find the function corresponding to the previous graph. So we know at E0, n is equal to 1. So let us just plot the table for this, at least for the values that we know. No, I mean, we can plot it for other values also. So we have energy over here and number of states at or below that level. So we have E0, 1, 4E0, we have 2, 9E0, we have 3, 16E0, we will have 4, 25E0, we will have 5 states at or below. So what is the function? Like, what is the relation between E and N? From this, from observation, we can say it is nothing but square root of E by E0. N is equal to square root of E by E0. Because when E equal to E0, we get 1. When E equal to 4E0, square root of 4, that is 2. 9E0, square root of 9 is 3. 16E0, square root of 16 is 4. So this function matches. So this is N. Now what I'm going to do is, I'm going to write the expression for E0. So that is square root of E divided by E0 is, in the previous slides I've defined it, it is pi square h bar square by 2ml square. So divided by pi squared h bar squared divided by 2m L squared. Further, this is again square root of, you know what, since writing a square root is very difficult, I'm going to go to rational powers. So this is 2m L squared E divided by pi squared h bar squared raised to the power half. So this is the square root expression. Now the third part is essentially we need to use the above function to obtain the density of states for a 1D system. So this is the function. This is the answer to part B. Now moving on to the next slide. We shall do part C. So part C is use N of E to get the density of states. So N of E, as we have seen before, is this quantity. It is 2m L squared E by pi squared h bar squared to the power half. So what I'm going to tell is d1d of E, that is the 1D density of states, is exactly this. It is dn by de. So whatever function we obtained here, the derivative of that with respect to E is the density of states. So we have this, we just need to differentiate this. Again, these are all constants, so I can just write this whole thing separately. Okay, I need to be more precise here. It is dn by de per unit volume. So you can ask what this per unit volume is. I will explain that as I finish this derivation. So e to the power half. Now when we do the, oh no, I can just write this as d by de of e power half, which will be the same constant L squared upon pi squared h bar squared into 1 by 2 square root of E. Yes, so yeah, now bringing the terms in, we can see that, oh yeah, this is power half over here. We can see that 1 by pi square h squared is a square, so square root of that will just give us 1 over pi h bar. So this is as it is. And in fact, and then 2m will be inside the square root. 2 can be kept outside, but since there is a 2 over here, what I'm going to do is I'm going to take that in here to make it 4e, and then so that will be 2m by 4e into L. So this L square I'm keeping it separately. Now you'll ask why. So square root of L square is L, and this is whole power half. So from this we will get our expression 1 by pi h bar square root of m over 2e into L. Now outside of this into L factor, this is the density of states that we know as the 1D density of states. So we know this from our slides. So this is d 1D of E. So this is the density of states for the 1D system. Now why did I say per unit volume? Essentially what this means is, for this we need to go back to question 1. See, as we are increasing now, I actually made a small, like I cheated a little bit here when I was representing this function. Essentially what I did was, this function is not supposed to be a continuous curve. It is supposed to be 0 until here, then go to 1, then stay 1 until here, then go to 2, then stay 2 until here, and then go to 3. It should move like a step function if I'm actually plotting it like a function. What I'm doing here is, I'm considering the cases where L can vary. So we are actually looking at the limit where L has become very large. We are looking in the limit where L tends to infinity. When L tends to infinity, as we have discussed before, the energy spacing between these points will come closer and closer and closer. Because of that, this stepwise function that we have can be represented by this curve that I drew. So in the limit L tends to infinity, this function is actually a proper representation. And therefore, what we will do is, we will divide this L to represent the fact that this is a density function. So that is why it's called the density of states, and it has a unit per unit volume, whatever the dimensionality of the system is. So here per unit length. Essentially, if I double the length, then I will have twice as many states, because the states will become that much closer. So twice the amount of states would have moved in. If the length is tripled, then thrice the amount of states will be available. So that is the understanding. So it is dn by de per unit length. So ultimately we will also divide by L. So that is why we perform the division by L. So this is the density of states for the 1D system. So for people who are familiar with some basic probability and statistics will know that this function that I drew here is a cumulative function. Essentially it says the number of points available at or below this value. So number of energy states available at or below E0 is 1. At or below 4 E0 is 2. At or below 9 E0 is 3. So this n of E is the cumulative distribution function. So once you take the cumulative distribution function and take its derivative with respect to the energy, whatever quantity we get, again further divided by the volume of the system, is going to be the density of states. So that is the fundamental definition of the density of states. So let me go back to the slides here and quickly add and make an addendum. So it's a density function, and to add to that, it is the derivative of the cumulative function n of E. Now what n of E is, that has been defined at least for the 1D case. All the way down here. Okay, so this is actually true for 2D and 3D systems as well. For any system, in fact, all we have to do is write n of E and take the derivative of n of E. And taking the derivative and dividing by the volume of the system should give us the density of states. So that takes us to problem 3. Now in problem 3, I am going to make an addendum here. I am going to say for 0D systems as well. Okay, so this question should more or less help people, to those who are watching the video. Problem 3 should help you solve many of the assignment questions. If you have followed problem 2 and problem 3, the density of state questions in the assignment should become more or less approachable. So you are supposed to do it for 0D, 2D and 3D system. Okay, this is a comma which looks very bad. So yeah, what I'm going to do is I'm going to do the 0D part last. So first I will start the what is it called, the 2D system. So shall I use it here? No, I will begin a new slide. Or no, I'll actually begin from here itself. So again, what we have to do is, so part 1, I'm going to do the 2D system. So for 2D system, I need to find N of E, number of states available at or below a given energy level. Okay, so now what is ES? Now here I have told that this is a square well. Now what is a square well? It implies Lx equal to Ly equal to Lz. So this is essentially a box where the edges of the box are all equal. So in a 2D system, I will only consider 2 of these dimensions. In our convention, I'm going to take Lx and Ly. And in a 3D system, it's all 3. And in a 0D system, none of these appear. So we will be having what is called we will be having a special case. So in fact, rather than stenciling it in here, let me just quickly type it so that it becomes clear. Oops. 0D. Yes. Zero D, 2D, and a 3D system. Yeah, and 3D square wells. Okay, so now essentially what we have to do is we have to find the value of N of E. So how do we go about doing this? First we need to find out what En is. So N of E needs to be found. N of E is needed. And we know E, now there are going to be 2 N's. So it's going to be E Nx comma Ny. Okay, because there are 2 dimensions here. So that's going to be Nx squared plus Ny squared times pi squared h bar squared by 2m L squared. I'm going to say all these 3 are equal to L. Okay. So in a 2D system, the energy is going to be E naught into this, E naught into this. Since the lengths are all the same, I'm pulling the factor out common. Again, Nx comma Ny vary from 1, 2, 3 and so on. So they cannot have the 0 value. Is equal to 1, 2, 3 and so on. Okay, so that is that. So now let us look at what are the available energy values. Let us not look at how many states are there, but first let us try to write the energy values. So first the lowest possible energy value is where we have Nx equal to Ny equal to 1. So we have Nx comma Ny equal to 1. So that En corresponds to, or rather E is equal to. So even here I can define this quantity to be E naught. Okay, because since the lengths match, all energies will be in terms of this quantity right here. So I'm going to call this one again for this problem. I'm going to call this guy here E naught. Okay, so over here I know this is E is equal to 2 E naught. Now see, the lowest energy value is no longer E naught, it is 2 E naught. Second energy value is where Nx equal to 1 and Ny equal to 2. That will correspond to 2 squared plus 1 squared. So that is 5 E naught. But what is to be noted here is that, oh no. But this is not all. What happens is, I can also have the case where nx is equal to 2 and ny equal to 2, and even then, sorry, ny equal to 1, even then E will be 5 E naught. So the fact that this happens means there is what is called a degeneracy. Okay. So essentially what is happening is, as we are going to higher and higher energy levels, multiple values of nx and ny can correspond to the same energy levels. So this is one very straightforward case where we have two different representations of 5 E naught. Okay. And like this, what to say, like the system will keep on growing. But now we shall try to sketch the curve. And here I will tell you why I did not consider this problem to be, why I didn't try deriving the density of states using our previous method for this problem. So essentially what happens is, so the energy values are 2 E naught and 5 E naught. So let me just write the value E and N of E. So 2 E naught, we have one state. Now at 5 E naught, we have two states which have 5 E naught, and then we also have the 2 E naught state. So that is 3. And the next energy value, if we look at this expression, we will see that it corresponds to the case where we have 2, 2. In that case, we will have what is 8 N E naught. So in 8 N E naught, we will have 4 energy levels, because 8 will correspond to 2 plus 2. Now interchanging the order there does not change the state, because nx is equal to 2, ny is equal to 2. So there is no degeneracy. So we have only one state, and we have 3 states from before, so it is 4. And then the next energy level is where we have one of them is 3, the other one is 1. So I will just write nx and ny over here in brackets. So this is 1, 1. I will also write like nx and y just to make sure it is understood. So here we have 1, 2 and 2, 1. Both of them are present here. Over here 2, 2 is the only addition. And the next value is when we have 3, 1. So that is 3 square plus 1 square, that is 10 E naught. Now again, oh, did I write 8 N E naught? No N over here. So this is 8 times E naught. The next energy level is 10 E naught. And in that we have 3, 1 and 1, 3. So that will be 2 states over here, 4 before that. So we will come to 6. So on and so forth. So we can keep on moving like this. Now, what does this tell us? What this will tell us is essentially this. So usually what will happen is, when we arrive at a particular energy level in general, at least 2 energy states will show up. There are some exceptions. As you can see, 2 and 8 have only one representation. And in fact, if I go all the way down to say something like 25 E naught, not 25 E naught. Let me go even further down. Let me go all the way down. 25 E naught is not allowed here. Let me go to 50 E naught. So in between there are several energy levels. Now how many possible, I don't know what the cumulative distribution at 50 E naught is. I'm not going to calculate that. I mean, we can calculate that, but we don't need to do that. We don't have to do that much math. So I'm not telling what is here, but 50 E naught corresponds to, so 50 can be written as 49 plus 1, which is equal to 7 squared plus 1 squared, or it can be written as 25 plus 25, which is 5 squared plus 5 squared. So this thing is going to have 3 possible states here. It is going to have 7, 1, 1, 7, and 5, 5. So whatever the value of the distribution here up until this point was, it will become that plus 3. Whatever the value here before 50 E naught was, it will become plus 3. So what we will see is more or less on an average, I either add 2, 1 or 3. So on an average, each energy level adds 2 states. So you know what, let me just evaluate one energy level after 10 to prove, to just establish the point. So this corresponds to 3, 1 and 1, 3. We have done 1, 1, 1, 2, 2, 2 and 3, 1. So the next state we can go to is 3, 2. So 3, 2 will be 9 square plus 2 squared, sorry, 3 square plus 2 square, which is 9 plus 4, which is 13. So the next energy level is 13 E naught, and we will have 2 more states, that is 3, 2 and 2, 3. So this is 8 over here. So what we are seeing is, in a way, oh wait, yes. So on an average, every subsequent energy level is adding 2 states, 2 states to N of E, capital N of E. Okay, so if I were to try to plot this graph, what will it look like? If I were to try to plot this graph, as we are moving from one energy level to the next, okay, we will have, okay, for the first case we have only 1, but after that the next one will actually have, so let me say this is 1, oh no, not minus 1, this is 1. Yeah, so this line here is N of E, and we have E over here. Okay, so in this case, like, so initially at the lowest energy value we will be at 1, but when we go to the second energy value we will be slightly above at 3, then we will be over at 4, and here the spacing between the energy levels is not uniform. Okay, so that needs to be understood. So this is just for this case, I'm going to write it as 2 E naught, 5 E naught, and 8 E naught. So you can see that up until here it is uniform, but then it becomes 10 E naught. So here the spacing is actually not uniform. So it is jumping by 3 E naught, jumping by 3 E naught, then jumping by 2 E naught. So the jumps are also kind of jittery, and simultaneously we also have, on an average, it increases by 2. So it will go up to 3, then suddenly it will either go to 4 or it will go to 6. So every step on an average I'm adding 2. So that function is actually a straight line, a line of a complex, constant slope on an average. This implies N of E is linear, not linear, it is linear in E, which implies N of E is proportional to E. Therefore, dN by dE will be proportional to dE by dE, which is a constant, will be proportional to 1, or one can directly write this is equal to a constant. So that is all this says. Like, when the density of states is constant, what it means is the number of energy states as the energy increases will increase linearly. So the slope of this function, whatever it is going to be the density of states. So this is linear. So the number of states that are present is going to be linearly, and in the previous case it was, so let me write here, n is proportional to square root of e. So even though I don't know the exact function, the density of states function, I will know it should not have any e dependence. Or alternatively, what happened to my pointer? Oh, it's there. Okay. Just 1 second. Yes. So all the way down here. Yes. So or dn by de is proportional to e to the power 0. That is another way of saying it is like proportional to 1, because e to the power 0 means it does not depend on the energy. In the previous case, since this depended on square root of e, we know that the density of states will be the derivative of that, therefore it is proportional to, so I can write here it is proportional to 1 over root e. So and here, although we derived the proper density of states function. Okay. So that is all this means. So now we can see what happens in the case of d equal to 3. We can guess what is happening in the case of d equal to 3. So whatever function we get, it is going to be more or less, not more or less. So yeah, before I go to the, let me do this first. So the 3D case, so 3D, again, in this case, E is equal to nx square plus ny squared plus nz squared into E naught, where E naught is the characteristic energy of the system. This is a square well, so Lx, Ly, Lz are all equal. That is why I am able to write this. So let me write that here for a square well. Okay. Lx equal to Ly equal to Lz. Okay. Now, again, the lowest energy values, this time it's 3 naught, and so I have E over here, and so I can write it as energy and N of E. So 3 naught, I have only one state, and here I will write an X and Y and Z. NZ. So this is 1, 1, 1. The second value is when any one of this is 2, so that will correspond to 6 E naught. So that is 4 plus 1 plus 1. So there we will have 3 possible states, because any one of this can be 2. So the cumulative function will jump up to 4. So that is 1, 1, 2, 1, 2, 1 and 2, 1, 1. So like this we can keep going further and further and further. What is essentially happening here is the degeneracy is increasing, because I have now 3 values of n which can either match or mismatch. So what will happen is, and again the previous case that I explained here, where there are some numbers which have more than 2 expansions, that problem will also start occurring here, which implies as and when E goes, the number of energy state configurations it introduces will become larger and larger and larger. If, like, you can actually, anyone who's like programming savvy can write a program to plot these values of nx, ny, and z, like keep varying them over, say, vary this from 1 to say 20 or something, each of these, calculate this quantity and create a frequency table, like what values of energy are occurring with what frequency, then what you will see is something like this. So what you will see is a function that will look something like this. So it will not be quite quadratic, but it will be slightly, it will rise slightly faster than a linear function. So if this is my quadratic function, let me say this is y equal to x square. Let me say this is, or rather let me not say this is x squared. Let me say this is e squared, because here we are looking at functions of e. So this is e increasing in this direction, and we have n. And let me use a different color also, so that confusion is not there. So it's going to rise faster. So if this one is proportional to e squared, and let me say this is the straight line. This is the straight line. So this is proportional to e. The graph that we obtain for the 3D cumulative distribution will be between these two at all times. So this is actually proportional to e to the power 3 by 2. So doing this by hand is it was difficult for the 2D case. It is much more difficult for the 3D case, but you can actually write a program to do that. I will see if I can, if I have time, I will see if I can write a program for this and share it with, at least share the results next tutorial, not stand, permanently. So if I have the time, because currently I'm also occupied with some other work, if I get some time, I will do that, and you can also see that what I'm saying here is actually happening. So the function will more or less look like this. It will be proportional to e to the power 3 by 2. So since n of e is proportional to e to the power 3 by 2, dn by de will be proportional to e to the power 1 by 2, because the derivative of this is e to the power half. So the density of states will be a square root function. Therefore, we have our final, this is the most important set of results. So we have the dimensionality. So the dimensionality, it is 1, 2, 3, and we have the dependence on e. So this is d of e. So d of e is proportional to e to the power minus half. In this case, it is proportional to, so this we have derived. So this has been fully derived in this session itself. Here it is proportional to e to the power 0, not been derived, but an approximate argument has been given, and likewise for this it is going to be e to the power half. So when I go from 1 dimension to 2 dimension to 3 dimension, we jump from minus half to 0 to half. So every time there is an increase in half in the exponent here. So we start from minus half plus half, which is 0, plus another half, which is this. And correspondingly, if I were to add a new column here, n of e, I know this is proportional to e to the power half, this is proportional to e, and this is proportional to e to the power 3 by 2. Again, as expected, it starts from half and there is a jump of e to the power half in each case. Now, this is to be expected because in a single dimension system, n of e is proportional to e to the power half. If in a two-dimensional system, what we are doing, we are actually having energies corresponding to k values in x and y direction. Those energies are adding up. So the energy dependence will be the sum of those two, the exponent will be the sum of those two values. So in 2 dimensions, it is going to be the square of whatever was present here. When I am adding a third dimension, another factor of e to the power half will be added to this. So it is essentially that we can actually generalize this. If we have an n-dimensional system, n of e will be e to the power n by 2, and correspondingly the density of states will be the derivative of that. So it will be e to the power n minus 1 divided by 2. Sorry, n by 2 minus 1, not n minus 1 divided by 2. It will be n by 2 minus 1. Okay, not representing it here because we are not considered with multidimensional systems. Like they are not physical, they are only theoretical constructs, so we need not worry about them. However, a zero-dimensional system is not unrealistic. So we shall try to spend some time over here because this is important, and this will also have implications in the later weeks. So we have a zero-dimensional system. This might look like OD. So let me be clear here and write a zero-dimensional system. So what is a zero-dimensional system? So this is what I'm writing as 0D. So what is a zero-dimensional system? A zero-dimensional system is something that has no volume. It is treated as a point object. So zero-dimensional systems are treated as point objects. So in physics, these are elementary particles. So I mean, we need not even say elementary particles. These are particles like electrons and holes. So we have electrons, we have holes. So these are treated as zero-dimensional objects because they technically, like, we do not care about their size because this is a quantum mechanical treatment, and in fact treating them as point particles and applying the physical laws to them even gives us experimentally correct answers. So the understanding that these are point particles fundamentally is not very far-fetched. It actually gives us meaningful results. It is also possible to treat atoms as a zero-dimensional system because a single atom is a single atom. Like it's a predefined system. I cannot change any properties of the atom very easily without like modifying the atom itself. So atoms are also zero-dimensional systems. Now, what happens in the case of zero-dimensional systems? So in a 0D system, all energies are quantized. So there are no continuous energy levels in a 0D system. So atoms, even molecules, can be treated as a 0D system. Can they be? No, they can't. They can't. I'm sorry. So I'm not going to write molecules over here because molecules can have other properties also. But yes, up to atoms, it is perfectly fine to treat them as 0D systems. So in this case, all energies are quantized. There are no continuous energy levels anywhere. So this can be seen. Evidence is atomic spectra. So atomic spectra always has like narrow bands or spectral lines. We don't have like wide band smears of energies in the case of atomic spectra because the atomic energy levels are more or less quantized for the entire span of the spectrum. So, but of course we will see what is changing there. And other than this, size change has no effect on delta E because I can't define a size for this object at all. It is zero dimensional. So I can't say I'm making the length double. I can't say I'm making the height double or triple because double or triple of 0 is still 0. So there is no size scaling that is possible. So here, even before we say size change, this is technically impossible. Okay. So this is technically impossible, and because of that, there are no size change effects on the value of delta E, which also implies that density of the energy levels will not change. Because what did I say for the 0D, sorry, for the 1D case? This is a graph I drew for one particular length. In the limit L tends to infinity, these points will come closer and closer and closer together, and I will get a nearly continuous graph that looks, so essentially, as L tends to infinity, we will get a continuous graph that is the square root x function. Okay, so it will be something like this. So this is square, not E, x square root E. So this is with E, and this is n of E. This is not the density of states function, this is the cumulative function. This is the number of states at energy less or below. So this is in the limit L tending to infinity. When L becomes very large, this point graph that I drew will become this continuous curve. But for a 0D system, that will never happen. So the density of state is actually a point graph always. Okay, so let us consider a case where, so now what I'm going to do is find the try to do n of E for a 0D system. So for that we also need what the value of the energy is. So for that what I'm going to do is I'm going to consider what is called the Bohr model or the Rydberg model of the atom. So now we have a 0D system where En is equal to some minus E naught by n squared. So this comes from like the Bohr model derives this of the atom, or it is also called the Rydberg atom because the original expression I think was due to Rydberg. So this is also called the Rydberg atom. Or this is also the energy levels we get from the hydrogen atom, like when we solve for the hydrogen atom, the quantum mechanical problem for the hydrogen atom, when we do when we disregard the effects of spin and so on and so forth. Okay, so this is the value of energy that we get. So first and foremost, let us try to find out what delta En is. So that is En plus 1 minus En. So that is equal to, let me pull out this minus E naught over here. So it is 1 plus 1 by n plus 1 the whole squared minus 1 by n squared. Now what we will see is that this is n squared minus n squared plus 1. So that will be, let me just write it. Why am I'm writing it, so let me just go ahead and write it. So this is n squared minus n plus 1 whole squared divided by n squared into n plus 1 squared. So this quantity is minus 2n, minus of 2n plus 1. So this minus and that minus will cancel. So we have delta E is equal to 2n plus 1 divided by n squared into n plus 1 whole squared. So this is delta En. So what happens is, as n tends to infinity, delta En tends to 0. Meaning at higher and higher energy levels, two consecutive energy levels become nearly like close. So when I said all levels are quantized up to a certain point. So beyond that, of course, a continuous spectra exists. Okay, but even then it is not like properly continuous. It will still have a discrete gap, but that gap will become smaller and smaller and smaller as we increase n. Okay, so now how many states does this system have? How many states does this system have? So let us try to find what n of e is. So what happens to n of e is, so first we have minus e naught. Oh no, this is e. So let me just write that table here. Okay, so we have energy and I have n of e. So we have the first energy value, that is minus e naught. There is one state. Then I have minus e naught by 4. For that we have two states. Then we have minus e naught by what is this? 9. For that we have 3 states, and so on and so forth. So what I will do is I will draw a graph of minus e. Okay, because this is going in the negative direction. Of course, before I go any further, why are these values negative? They are negative because these are bound states. So these are bound electrons. So okay, so the graph here will be so what I'm writing here is this is minus e, this is not e. So minus e is increasing in this direction. So we will have so what we will essentially have is I will have e naught over here, then I will have e naught by 4, then I will have e naught by 9, then I will have e naught by 16. So essentially what will happen is the points will be going like this, further and further and further, and they will go closer to 0. And how will my density function look? Until here there is only one state, and at this point there are 2 states, and at this point, so what I'm going to do is I'm going to like enlarge this graph somewhat just to avoid this essentially I'm going to like change the scaling of this graph. Assume that this is like a semi-log plot or something. Okay, so I'm not going to plot this in the linear scale because it will look very skewed. So essentially what we will have is, yes, so we will have, let me say this is e naught by 4, this is e naught by 9, and so on. Okay, so what will happen is it will be 1 up to here. So this is 1, 2, and 3. So this is a linear scale more or less. So it will be 1 up to this point, then it will go to 2, it will be 2 up to this point, and then it will jump up to 3. So the function will be a step function. So it will increase in steps. Then when we go to e naught by 16, it will jump up again. Now what we have to see here is that this quantity delta En tends to 0. So this jump will start happening faster and faster and faster. However, since there is no size dependence here, previously what did I say? When I have a 1D system, as L tends to infinity, I will get a continuous curve. Even in a 2D system, when Lx and Ly both tend to infinity, I will get a straight line. In a 3D system, when the volume Lx, Ly, Lz all tends to infinity, we will get this kind of a curve, e to the power 3 by 2. But for a 0D system, nothing is going to happen. This is the only curve we have. So this is n of e. We have nothing else. So what we have to do is we have to do a differentiation of this step function. Okay. So that has to be understood. And that is all I will say, because this will lead directly to an assignment question. So whatever I have told before, apply it to this graph and you should be able to solve at least one assignment question very well. But on that note, let me just make one more addition here. So let me rewrite a table that I wrote before, dimensionality, and here the dependence of n of e. So what did we say is for this is e to the power half proportional to e to the power half. For 2 dimension, it is proportional to e to the power 1. For 3 dimension, it is proportional to e to the power 3 by 2, yes. So every additional dimension introduces a factor of e to the power half. So what happens for a 0D case? This is proportional to e to the power 0. Like the density actually does not depend on what energy I am in, because the energy does not scale with the size. The energy remains fixed. So there is no scale variation, there is no size variation, and because of that the cumulative distribution is independent of the energy. So it is just a predefined step function for a 0D system. And conversely, what will happen is density of states. So we know over here this is proportional to e to the power half. We know this is proportional to e to the power 0. We know this is proportional to e to the power minus half. And over here, what it is going to be proportional to, I will not tell. Like it is actually not possible to define that over here. That is the challenge. But what we have to do is we have to, like, e to the power 0 implies the function is constant. As you can see, this is a constant. It's a constant till here, it's another constant till here, it's another constant after this, and so on. So it is a series of constant functions. So people need to know how to take the derivative of this function and where and what this derivative will be. It is pretty easy to look up. If you look that up, you have the answer to one assignment question. I will not say anything more. So we have completed problem 1, 2 and 3. Yes. And that brings us to the end of our discussion on density of states. So now we move on to our next topic, which is the Fermi-Dirac distribution. So the Fermi-Dirac distribution, it's a probability distribution function. Quite simply, it is just that. And it applies to a collection of fermions. So fermions are elementary particles, or even like non-elementary particles, compound particles can also be fermions. And they obey this statistical relation. There is a connection between the statistical relation and the spin of the particle, and that is called the spin statistics theorem. So when we talk about fermions, we mean spin half particles. So these are spin half particles. Most famous example is the electron, of course. There are many other examples, such as your proton or muons or any other most elementary particles that you consider that you might encounter early on in your studies of physics are fermions. Neutrinos are fermions, and so on and so forth. So these statistics, when I have a collection of electrons, their energy distribution will follow this function. So this is a probability distribution. Therefore, as a result of this, integral 0 to infinity of this quantity f of e dE. I mean, technically speaking, should I use negative energies? I am not using negative energies for a reason. Essentially, whatever the lowest energy level of this system is, that is taken as the 0. So when I write 0 here, this is the lowest energy of the system, because energy levels can be scaled, which is why I did not write this integral in the main slides, because it's a very iffy thing to write. But from 0 to infinity, This is 1 because this is fundamentally a probability distribution function. So what does this tell us? What this tells us is if we have a collection of electrons, so I'm not going to talk about fermions, I will only talk about the electrons in this case because that is what we are interested in. The electron, if I have a collection of electrons, then in a system which has energy values, energy levels in it, so there is some physical system. It can be a potential well, it can be like a 1D, 2D, 3D potential well, it can be the channel of your devices, so it can be a 1D, 2D, 3D channel, it can be anything, it can even be an atom. So the question that is asked here is, what is the probability the energy level corresponding to energy value E is occupied? That is all. So this quantity f of E, what is it a probability of? This is an occupation probability. Is an electron there or not? Okay. So this is the occupation probability. Now the quantity mu that I've written here, in your slides and in textbooks, alternatively it is also referred to as EF, is called the chemical potential or the Fermi level of the system. So it is a property of the system, like it is a property of the system in which the electrons are and the number of electrons. Okay. So this is like the structure of the environment in which the electrons are confined and the number of electrons. Increasing the number of electrons will increase the Fermi level. This is universally, like this is valid always. If I don't change my system and if I'm simply increasing the number of electrons in it, the Fermi level will rise. Okay. Now there are two possible definitions of the Fermi level. So one definition is it is the highest energy level occupied by the system. Oh, I should have written this occupied. So two occupied here, one too many. Yeah, system at temperature 0 Kelvin. So if the temperature were 0 Kelvin, the highest energy level that is occupied by this collection of electrons is the Fermi level. Okay. Alternatively, it can also be defined as the lowest energy a fermion or an electron needs to have to become a part of the system. So this is like when we treat it as the chemical potential, this is the definition that we use. This is from thermodynamics. More precisely, or statistical mechanics, like thermodynamics is a very loose term. So this comes from statistical mechanics, this definition. So physics students might be familiar with this definition. And more precisely, this comes from, in statistical mechanics, the study of what is called a grand canonical ensemble. So when we study about grand canonical ensemble of fermions, this quantity, the Fermi energy or the Fermi level, or it is also called the Fermi energy or the chemical potential, comes into play. But even if we do not consider a grand canonical ensemble, if we are considering a system where the number of particles does not change, the first definition holds. It is the highest energy level occupied by the system at 0 Kelvin. Okay. So what does this mean? So before proceeding any further, let us look at some important properties of the Fermi-Dirac distribution. Okay. So what happens at 0 Kelvin? So at 0 Kelvin, what does this imply? No energy is available to the system from the environment. Okay, so that is what 0 Kelvin means. 0 Kelvin means no energy can come from outside because there is no energy available from the outside. Okay. So what happens? Let us say I have a system here where I have energy levels. Now let me say I have a system like this. Okay, and so far what we have, the one thing that we haven't spoken about is the Pauli exclusion principle. Might as well use it here. Okay, so I have a system with energy levels that are distributed like this. Let me say in this system, so I have energy levels 0, 1, 2, 3, 4 and so on and so forth. Okay, now let us say I have a collection of 6 electrons. Okay, so when we have a collection of 6 electrons, how can we fill this? Now each state can accommodate 2 electrons of opposite spins. So I am going to represent them by an arrow this way and an arrow this way. An arrow this way and an arrow this way, an arrow this way and an arrow this way. So when no energy is available from outside, this is how I can fill the system. I cannot put a third electron here because electron can have either spin up or spin down. Now if another spin up electron comes here, then it will violate what is called the Pauli's exclusion principle. So what does Pauli's exclusion principle say? Pauli's exclusion principle, I'm not giving a formal statement here. In essence, what does this principle tell us? It tells us no two electrons, in general fermions, may have the same set of quantum numbers. Now I know I'm using some terms that I haven't used before, but the thing is we have been using these things without naming them. So what are quantum numbers? Quantum numbers are nothing but energy levels. So when where is it? Where is the 2D case? Yeah, this one here. So when I write nx, ny, these things are actually the quantum numbers. These are the quantum numbers. That is it. So when we are considering the spin of the electron, of course that also becomes a quantum number. So spin up and spin down have their own quantum numbers. It can be +1, -1, +half, -half, however we are defining it. The thing is, no two electrons may have the same set of, like all the quantum numbers cannot match. At least one has to be different. So when they are at E0, yes, the energy quantum number is 0. But the spin is different for these two. If I introduce a third electron, it will either have to be upspin or downspin, which means there will be 2 electrons whose all quantum numbers will match, which is not allowed. So when we have 6 electrons, this is the only way in which we can fill it. There is no other way in which we can fill it when no extra energy is available. So this implies, like generally what we will assume is when we have a system and we cool it to 0 Kelvin, it will all go to the lowest energy, but that may not be the lowest energy globally, especially in fermions. They will never all go to the ground state. They will actually occupy a set of states up to a certain point. So the highest energy that is occupied at 0 Kelvin can be defined as the Fermi level. So this is the Fermi level of this system. Okay, now there is another case where we can have 5 electrons, but I will come to that much later. Like 5 electrons or 7 electrons or something like that, then what happens to the Fermi level? What happens when we are adding more electrons? For instance, if I add 2 more electrons, then the Fermi level will jump to the next one. If I add 1 more electron, the Fermi level will again move up. So that is what I said before. Increasing the number of electrons in the system will increase the Fermi level. Always. Okay. So that is the fundamental property. So at 0 Kelvin, what is this distribution function? So what does this function look like? So the function tells us the probability that a given state is occupied. So here I will say this is energy state 0, energy state, or rather energy state 0, 1, 2, 3 and so on. So energy state 0 is definitely occupied, energy state 1 is occupied, energy state 2 is occupied, after that nothing is occupied. So in fact let me draw this graph slightly better. The axes are too big and the graph is too small. So yes. Okay, so this is 1, this is 2. Yeah. So it's going to be like this. It's going to be some value over here. I'm not telling what that value is. In fact, you can find out what that value is because this is a constant. This length, I'm calling it as 2. The area under this curve, which is this integral over here, has to be 1. Therefore, this point, if this is 2, it will be the reciprocal of that. So whatever this length is, it will be the reciprocal of that. Okay. So in that unit, typically we call this 1. So here this is not an absolute scale. This is scaled in inverse of energy. Okay. So this is an inverse of energy scale. So in that, whatever this length is, it will be 1 by that quantity. So this is the Fermi-Dirac distribution at t equal to 0. You can see that quite directly from here. So essentially when t tends to infinity, this quantity will become 0. Will it become 0? Yes, of course it will become 0. So f of e will become 1. Okay, so that is why in that normalized unit we say f of e is 1, which implies the probability of energy states below this being occupied is 1, which is why it is a probability measure. Okay, so state 0 is definitely occupied, state 1 is definitely occupied, state 2 is definitely occupied, state 3 onwards are unoccupied, they are empty at 0 Kelvin. Okay, so now what happens when we increase the energy? When we increase the energy, typically the electrons will be allowed, like, increase the temperature, not increase the energy. When we increase the temperature, so this is at t equal to 0. So I'm going to say this is t equal to 0 K. When the temperature increases, what will essentially happen is some of the electrons here will get some energy from the environment. They will get thermal excitation to move to some of these higher levels. So in that case, what will happen is the probability of the electrons being found in these levels will increase and the probability of the electrons being found at this level will slightly come down. So in those cases, as temperature increases, the graph will look something like this. Okay, it will look something like this. Oh, I actually managed to draw a continuous curve. Yeah, it will look something like this. Yeah. Yes. And now I have fudged it, which again manages to erase itself completely. Yes, so it will look something like this. Now, as and when the temperature increases, something will happen here. Again, I'm not going to draw that because that is an assignment question. However, I will tell you this. When t tends to infinity, when t tends to 0, this quantity becomes, when t tends to 0, this quantity becomes, this whole quantity becomes, wait, did I make a mistake? No, I didn't make a mistake. Yeah, it's fine. So when t tends to infinity, this exponent will start becoming 0. Now when this exponent is starting to become 0, this quantity will become 1. So what is essentially happening is the energy dependence is lost. because when t tends to infinity, E minus mu by kBt will become 0, which implies this thing will not have an energy dependence at all. F of E will be independent of energy, in which case this graph will be a constant for all values of energy. So as t tends that much, I am willing to say, as t tends to infinity, this is what will happen. So this is T greater than 0 Kelvin, and this is T equal to infinity Kelvin. This is never possible, but this is like, this is a theoretical instance. Yeah, infinity Kelvin. Not going to happen. So yes. So as temperature increases, the graph will obtain this kind of a shape. Ultimately, when t tends to infinity, the graph will become a flat line for all values of energy. Now, where that point is, we are going to see. Yes. And this figure should give you a clue to solve one of the assignment questions in week 3. Okay. Again, I cannot explicitly solve the questions, and honestly, I cannot give a bigger hint than this. So, oh yeah, yes. So, Kunal Karan has, I'm sorry, I did not read the message. Another example for a 0D system, yes, are quantum dots. So, from the device standpoint. So, I'm sorry I did not acknowledge that before. So, quantum dots, yes, are treated as artificial atoms. So, quantum dots are sometimes called artificial atoms. Yeah. Yeah, like since I've been like only reading up the physics part for these sessions, I've kind of forgotten the devices part. So, apologies for that. Okay, so this is what happens. Now, what you can see is this. All these three curves are magically somehow intersecting at this point right here. They're all intersecting at this very important point. And from our previous exercise, we know what this point is. This is the Fermi level. This is the Fermi level. So somehow every Fermi-Dirac curve, no matter what temperature it is, will pass through this point. So the first question we should ask ourselves is, what is f of mu? F of mu is 1 over 1 plus exponential mu minus mu divided by kBt. That kB is the Boltzmann constant. This is 0 now, and therefore this becomes half. So no matter what the temperature is, because this becomes 0, so any effect the temperature might have on this is nullified. So no matter what the temperature is, the value of the Fermi-Dirac function, the Fermi-Dirac distribution function at the Fermi level of a system will always be half, which implies this straight line should also intersect through this. Therefore, this point is also half. Okay. So now what does it mean at infinite temperature? At infinite temperature, it means the electron can be present at any energy level because it has potentially infinite energy accessible to it, which implies it can get excited to any energy level in this system, which means all energy levels have an equal probability of having an electron in them. They also have an equal probability of not having an electron in them. So probability of occupancy is half across the board. So that is why when t tends to infinity, f of e is half for all energies. So f of e will become f of mu essentially for all energies. So these are the properties of the Fermi function, at least the properties that are required for the coming week's assignment. So let us do two numerical problems. So first, what we need to find out is find the probability of finding an electron at an energy level 5 times kBt above the Fermi level of a system. So what we are told is we have the Fermi level, essentially we have EF over here, or rather let me write mu because I'm using mu. Okay, so I have a series of energy levels below that. Again, I don't care about the spacing, like they can be whatever. And I have, why am I continuously writing EF? And I have the Fermi level mu. Okay, so this is mu. Now the question is, I have an energy level over here above, which is 5 times kBt. So kBt has units of energy. So at a given temperature, what is the probability of finding the electron here? Essentially, what is the occupancy probability of this energy level? So answer A is nothing but f of mu plus 5 kBt. No, T should be above. Okay, so whenever one is asked to find the probability of a state being occupied, it is just this. Okay, so it is just this value. So that is 1 by 1 plus exponential of mu plus 5 kBt minus mu, let me write that correctly, divided by kBt. Now the mu and mu cancel out. Oh, let me not do that. People who are just reading the slides will not be able to make head or tail. Okay, so who are not like watching the videos and are simply just reading the slides will not be able to understand what I have written here. Although I would really like it if people also watch the video while solving these things. So now that is nothing but, now again, this and this will cancel each other out, and kBt due to division will also cancel each other out. So this is nothing but 1 by 1 plus e to the power 5. So this quantity e to the power 5 will be like, it's slightly larger than 32, which is 2 to the power 5. So e to the power 5 will come out to be, just one second, I have this value written down. So that comes out to be just one second. Yeah. Yes. Yeah, so that will come out to be, what is approximately 6.7 into 10 to the power minus 3. So in percentage, what is this probability? Essentially, all you have to do is multiply by 100. So that will still be 6.7 into 10 to the power minus 1, or 0.67. 0.67% occupancy. So percent chance to find an electron. Okay. So whatever energy you have, you just substitute it over there. So the probability of finding it there is less than 1%. So it is, in relative terms, it is very rare, because what did we see? Below the Fermi level, like this graph over here, below the Fermi level, it is more or less 1 for a good range. So compared to that, 1% at 5 kBt is nothing. It is very small compared to the ones over here. So the probability of finding an electron at 5 kBt above Fermi level is actually very low. Okay, no matter what the temperature is, because as I increase the temperature, 5 kBt will also increase. Okay, so in general, we do not consider such wide energy ranges. Usually the acceptable range is 3 kBt. So Now, using this method, you can also solve for 3 kBT. I'm not going to explicitly solve it for obvious reasons. So that is the occupation probability. Now, the second question, this is important. Now, using this above answer, what can we tell about the probability that an electron with energy below the Fermi level can undergo excitation at the same temperature? Meaning, now what I am telling is, so if I draw the graph, okay, so no, just 1 second. If I draw the graph for the Fermi-Dirac distribution, okay, so it's going to be something like this, and it's going to fall. Let me put some more effort into this. That was a bit too lazy because this is necessary for the answer. So I have this. I really need to learn how to draw straight lines using this. Yeah, so let me say it's somewhere over here. So it's straight up to a certain point. Now this is at a finite temperature. And let me say this is, now you know why I'm drawing this line, because if this is 1, this is half. Okay. It will kind of bend over here. And as an added tool, I will also draw a line at the Fermi level. Okay, so in fact I will draw a red line. So I will draw this line over here. So this denotes my EF. Of course I haven't labeled the axis. Energy increases in this direction. This is EF or mu, and this is F of E. Okay. So what will happen is, it is going to do something like this. So it will be like this. Now I have not labeled the energy levels above and below this point. So the function will look something like this. Now, wherever this is corresponding to point like 0.0067, because it is 6.7 into 10 to the power minus 3. So that is 0.0067. So very close to 0. If we take some point over here and find out where that lies, let me use the other color here. So if we just trace that point over here, like it will be somewhere over here. So this point will be 5 kBT. Okay, so this point will be 5 kBT. Of course, greater than that, the probability becomes smaller and smaller and smaller. So after a certain point, it becomes so insignificant that it might as well be 0. Now the question is, what can we tell about the probability of a particle going excitation, undergoing excitation? Now what does that mean? What do I mean when I say an electron or a fermion is undergoing excitation? What I mean is that from this energy level, it has moved to a higher energy level. Now when will that happen? If that happens, what is going to happen here? The probability of occupancy is going to come down. So probability of excitation is actually 1 minus the probability of occupancy, because excitation means it is no longer at that energy level, it has moved from there to another level. So this is 1 minus probability of occupancy. And what is 1 minus the probability of occupancy? Like what is the probability of occupancy? It is the Fermi function. It is f of e, because probability of occupancy is f of e. As I mentioned over here, it is the occupation probability. So any energy level less than this will have this quantity here. So let us say instead of looking at E plus 5 kBt, I am going to look at E minus 5 kBt, EF minus 5 kBt. So in that case, what is going to happen? Again, I am going to write the same expression. So probability of excitation, which is 1 minus F EF minus 5 kBt. I have given up on mu. Don't know why I used it in the first place, but well, I used it. So 1 minus this quantity, okay. Now that is nothing but, now I know EF plus 5 kBt was e to the power plus 5. So in this case it is going to be e to the power minus 5. I am not going to expand on that. So this is 1 minus 1 plus e to the power minus 5. Okay, now this is going to be 1 plus e to the power minus 5 minus 1 divided by 1 minus e to the power minus 5, which is equal to e to the power minus 5 by, not 1 minus, sorry, 1 plus e to the power minus 5, which is equal to 1 by 1 plus e to the power 5. So the probability of occupancy at EF plus 5 kBt is the same as the probability of excitation at EF minus 5 kBt. So using that, you can actually guess a very important property of the Fermi-Dirac function about EF. No matter what the temperature is, around this point, the function will be antisymmetric. Essentially, whatever value I evaluate here, it will be 1 minus that over here. Like any point I pick here, whatever value I find, if I go to the point mirroring reflected about EF, it will be 1 minus that value. If it is 0 here, it is going to be 1 here. If it is 0.5 here, if it is 0.4 here, it is going to be not 0.4. Yeah, if it is 0.4 here, it is going to be 0.4 on the point that is symmetric about this. So this part is actually symmetric about essentially it is symmetric about a reflection about this point. Okay, if you reflect about this point, this entire function is symmetric. What I have to do is, I have to reflect it about this line once and then I have to reflect it about this red line. If I do both of that, I will get back my same f of e function. Okay, so that is a very important probability. So that was exercise B of the question. So essentially we found out the probability of occupancy and we found out that if E plus some value E naught has an occupation probability of some value, then that is the excitation probability for EF minus E naught. Same energy. Okay. So that is another property of the Fermi-Dirac distribution function. So this is part B also done. Now we move on to problem 5, which is the final problem for today, and with this we will end. So now the occupation level of some energy level. So here I am going to just solve this question as I am explaining it. So what I have told is, for some energy level, f of e is equal to 1 by 1 plus e to the power e minus mu upon kBt is equal to 1 by 4. This I told. Now if this is 1 by 4, what can we say? Is this for an energy greater than the Fermi level or less than the Fermi level? By just looking at this graph, we can tell that. Because if it is less than half, it has to be greater than Fermi level, because the value of the function lesser than under the Fermi level cannot be below the Fermi level. Like it cannot go less than half, because even at t equal to infinity, less than EF, the function has a lowest possible value of half. It cannot go below half. So probability 1 by 4 means it is somewhere over here. Okay. So is equal to 1 by 4. Now we need to find the probability of occupation for the same energy level when the temperature is doubled. Now how do we do this? It is actually, like, it might look very difficult because I have not told anything about the energy, I have not told anything about the temperature. I am just saying at some energy this is 1 by 4. Now I have doubled the temperature, what is going to happen? But this problem is not as difficult as it looks. Essentially this is equal to 1 by 4. Now I can write that 1 by 4 as 1 by 1 plus 3. which implies 3 is equal to e to the power e minus mu upon kBt. So I don't know what mu is, I don't know what t is, I don't know what e is, but I can tell what e minus mu by kBt is because this probability is given and I know the form of the Fermi distribution function. So this is equal to 3. That I know. Now what will happen to this quantity when the temperature is doubled? When T becomes 2T, T goes to 2T, what will happen? I will substitute T over here, so it will become that a factor of 2 will appear here. But a factor of 2 appearing here is nothing but taking the square root of this quantity. So this implies this whole quantity will become exponential e minus mu upon kBt whole power half. I already know this quantity is 3. Therefore, the square root of this will be root 3. Which implies, so this is at temperature T. Therefore, F2T for the same energy value is 1 divided by 1 plus square root of 3. And what is that quantity? It will come out to be this quantity will come out to be around 0.37. So this case, this is actually 0.25. So as we can see, increasing the temperature increases the probability of finding an electron at E greater than EF, because 0.37 is definitely greater than 0.25. So doubling the temperature implies the probability will also increase. The factor by which it increases can be done using this method. So this is how we can solve some elementary problems based on the Fermi-Dirac distribution function. So with that, we come to the end of this session. I did not see any doubts that were asked in the past week, so nothing to address over there, which is why I did more problems today. And whatever was asked in the chat I have addressed. So I thank you all for attending this session and for watching the recorded video. We shall meet again same time next week. Thank you.